Presenting advanced probability theory. Advanced probability theory one, that is, well, I've talked about probability before, but at the elementary stage. But you need to see those videos, my elementary probabilities 1, 2, 3. You also need to see my set 1, 2, 3 to be able to see this video and understand the contents of it. Now, the synopsis for this is probability spaces, in which I will discuss basic definition and properties, random variables, and distribution maybe later. Well, and after that, I will introduce R and the special packages of R on distribution. Now, the reference materials are just two. A book by Evans and Rosenthal, then another one by Dan Romick. The application that I will pay attention to is the statistical simulation. How is probability theory, probability spaces, distribution are used in simulation? Now, probability theory, it's like any other math course, except that it is a course that is used to model real-life phenomena. And it's not the only course that is used to do so. An example of a course that is also used to do so is differential equation. Except that in most cases with differential equations, the model is usually deterministic. But in probability theory, the model is stochastic. There are chances inclusive. It also recognizes noise. But how do you get to use probability theory to model? In fact, specifically in this case, how do you get to use probability theory to simulate? Let's start off by looking at algebra of sets or events. If is a universal set, you will soon find it to be a universal set or a sample space even. And we let script F be a collection of events defined on Then these two conditions will have to be satisfied for script F to be an algebra defined on It must be non-empty, meaning that the null set must be in it. And if there is a set A in it, not A must be in it. But not A, I discussed that in set theory. In my sets 1, 2, 3, please see those ones. Then if there is two events A and B in the script F, their union must also be in the script F. When these three properties are satisfied, you will say that script F is an algebra defined over Some texts will call it a field defined over. These two can be used interchangeably. They mean the same thing. Now, we are not interested only on algebra. We actually want sigma algebra. One additional property has to be satisfied, and that's the fact that when you have an infinite number of events in script F, then if their infinite union must also be in script F. If this property is satisfied alongside those former three, then what you have in your hands is a sigma algebra, not an ordinary algebra. Examples are this. We saw in set theory that the subset of events can be proper and improper. Okay, these are the improper subset of nothing and itself, the two extremes. And they constitute a sigma algebra. except that that's the smallest possible sigma algebra defined on Hom. The power set that contains all the subsets, whether proper or improper. The power set is also a sigma algebra and it's the largest possible sigma algebra defined on Hom. Okay, when we say space, we have a measurable space. When we have the pair Hom and scripted, where Hom is a non-empty set and scripted is a collection of the events defined on Hom. You see this pair is measurable. Whenever it's measurable, then the probability measure can be defined thereon. Long as it's measurable, the probability measure can be defined thereon. What the measure is this: it takes any event and it gives it a probability in the interval 0, 1. If the probability is 0, it is an impossibility. If the probability is 1, it is a shorty. I talked about impossibility and shorty in my video in elementary probability. Now, if we have an infinite number of events in scripted that are pairwise disjoint, pairwise meaning any two are disjoint, mutually exclusive. I explained that in my elementary probability. Then the probability of their infinite union will be simply equal to the sum of their respective probabilities. You know, when we had the generalized formula for cardinality, we also had from me the generalized formula for probability. And it was the case of the sum of the probabilities minus probability of their intersection. But when they are mutually exclusive, the probability of their intersections will each go to 0, leaving you with the sum of the probabilities alone. That's how the equality comes into being. Okay? Probability space is a triple Hom scripted P, where Hom scripted measurable. As such, probability measure can be defined on it. So this trial is what is known as probability space. Okay. Now we've been saying Hom. Like I said, Hom can be looked upon as a sample space where elements sets in scripted are actually events, random events. Please listen, go and see my videos on elementary probability. Now, additional properties. This trial is a sample space, then monotonicity is valid on it, meaning that if there are 3 events such that one is only contained in the other, then probability of the smallest is contained in is less than or equal to probability of the bigger. Subadditivity, if there are infinite events in scripted, then there are infinite union, finite number of events in there, then the infinite union will be less than or equal to the sum of their probabilities. Yes. These are changed a little bit. Less than or equal to. We saw equal to. Equal to we call if these ones are mutually exclusive, mutually disjoint. If that property is removed, then this is strictly less than or equal to this. Continuity from below and continuity from above. From ordinary real analysis, the function is said to be continuous at a point if it is unique. If the limit at that point is unique, I mean, the unit at that point is irrespective of the manner of approach. If it is transversed from below and transversed from above, it should be the same thing. Here, continuity from below is given this equation. Continuity from above is given that equation, this other equation, and the situation is that if the continuity exists at that instance, then these two must be the same. These two probability spaces If I throw a fair die once and ask you to collect the scores, probability of score 1 is 1 over 6. Probability of score 2 is also 1 over 6. Dot, dot, dot. Probability of score 6 is also 1 over 6. And if I add them up, it will be 1 over 6 times, and that will be equal to 1. But if I say, what is the probability of getting even score? You say 2 is even, 4 is even, 6 is even. The probability of 2, 1 over 6. Probability of 4, 1 over 6. Probability of 6, 1 over 6. Those three will add up to give you the probability of even score. Now, ordinary probability measure is, we saw it in elementary probability too. Cardinality of the event, right? We have event A, cardinality of event A over cardinality of the sample space. That's cardinality of event A. Now, choosing a random number uniformly in the interval 0, 1, uniformly. Uniform distribution. Now, if you want to take a number uniformly in, it means utilize uniform distribution to simulate. That's exactly what is being talked about. You recall for your uniform distribution, the least value is A, the highest value is B. But if A is 0 and B is 1, the uniform distribution, the PDF of the uniform distribution becomes 1. I intend to demonstrate this with, I will use Microsoft Excel to show you how to simulate using the uniform distribution. Okay, this is the farthest I intend to do, except that I still want to show you how to use the Microsoft Excel to simulate. If you launch your Excel, this is exactly what it will give you once you first open it. Now, it is focusing on cell A1. You just go to the formula bar and type this, equal to, then rand, RAND, open bracket, close bracket, hit the enter button. See what it has done. It has used a value in the interval 0, 1 to fill the cell A1. Let's assume you want more of this to be generated. See what it has done. It was a white cross before. By the time I put it at this edge, it gives me a black cross. At that instance, press your cursor and draw down your mouse. Maybe you want 10 of them to be generated. That's it. It gives you 10 distinct values that are in the interval 0, 1. This is simulation using the uniform distribution. Before now, statisticians used to use a table of random numbers. Table of random numbers. They open a page at random, take a column at random, take a row at random. The intersection of those two will give you the number that is being simulated. But this time we don't have to be carrying tables around. A computer application, e.g., Excel, can help us to simulate, at least using the uniform distribution. Later, we will see how we use R to simulate with other distributions that are relatively newer. That's the farthest I intend to go. Well, thanks so much for listening. Please like, share, and subscribe. Thank you. See you next time when I come up with another video in the series. Thank you.